Hello everyone, and welcome to Week 5, Petrophysics and Core Analysis. In this lecture, we move from drilling into the next critical step of subsurface evaluation, understanding the physical properties of reservoir rocks and what core samples can tell us about the reservoir. This topic is extremely important in petroleum engineering because discovering and drilling a well is only the beginning. To evaluate whether the reservoir can actually store and produce hydrocarbons, we need to understand pore space, fluid distribution, rock texture, electrical behavior, and rock mechanics. Today, we will connect very small-scale measurements from core plugs and thin sections to very practical engineering decisions such as reservoir evaluation, well placement, production forecasting, and log interpretation. Petrophysics is one of the bridges between geology, drilling, reservoir engineering, and production engineering. Let us first place today's topic in the overall course structure. In the earlier weeks, we covered the fundamentals of petroleum engineering, petroleum geology, geophysical methods, and drilling. Now we are in the appraisal stage, where the key question becomes, after drilling a well, how do we evaluate the rock and fluids we have encountered? This is why petrophysics and core analysis comes before well logging in the course schedule. First, we learn what the rock properties physically mean and how they are measured from core. Then, in the next week, we learn how to estimate many of these properties continuously from well logs. So this lecture is conceptually important because it provides the physical foundation for later subsurface evaluation methods. This week is organized into 5 major parts. First, we discuss basic petrophysics. Second, we introduce basic core analysis. Third, we examine what information can be obtained from core. Fourth, we move into special core analysis, which includes more advanced laboratory measurements related to flow, wettability, electrical properties, acoustics, and rock mechanics. Finally, we close with recap, next steps, and key learning points. As you go through this lecture, I would like you to keep one main question in mind. How does each measurement help us understand whether a rock can store hydrocarbons, transmit fluids, or produce economically? That question will help you connect the many concepts we discussed today. So, what is petrophysics? Petrophysics is the science of measuring and interpreting the physical and chemical properties of rocks and the fluids they contain. In petroleum engineering, this usually includes properties such as porosity, permeability, grain density, and fluid saturation. The slide also emphasizes that these measurements exist at different scales of resolution, which is very important. At the pore scale, we may observe tiny pore throats and mineral textures using microscopy or CT imaging. At the plug scale, we measure porosity and permeability in the laboratory. At the well scale, we interpret logs. At the field scale, we connect all of this to reservoir performance. So petrophysics is not just a list of properties, it is a framework for linking rock physics across scales and using those properties to make engineering decisions. This slide introduces porosity, one of the most fundamental reservoir properties. Porosity is the fraction of the total rock volume that is made up of empty pore spaces. In other words, if we imagine the rock as a mixture of solid grains and void space, porosity tells us how much of the rock can potentially contain fluids. Why is this important? Because hydrocarbons, water, and gas are stored in the pore spaces, not in the mineral grains themselves. A rock with higher porosity generally has more storage capacity. However, high porosity alone does not guarantee good production. A rock may have many pores but still produce poorly if those pores are not connected. So porosity tells us about storage, but not necessarily about flow. This slide introduces permeability, which tells us how easily fluids can move through the rock. While porosity is about how much empty space exists, permeability is about whether that space is connected well enough for fluids to flow. A rock can have porosity but low permeability if the pores are isolated or poorly connected. On the other hand, a well-connected pore system creates continuous pathways for fluid movement, which leads to higher permeability. This concept is central in petroleum engineering because production depends not only on how much hydrocarbon is present, but also on how easily it can be delivered to the wellbore. So here, the main teaching point is, porosity means storage, permeability means flow capacity. Imagine a reservoir rock filled with oil, gas, and water. What do you think controls the amount of water present in the pores, and how might that affect the production of oil and gas? Now we add another key property, water saturation, usually denoted by. Water saturation is the fraction of pore space occupied by water. Since the pore space may contain water, oil, and gas, the amount of water matters a great deal for hydrocarbon production. If water saturation is high, there is less pore volume available for hydrocarbons. In addition, water often occupies smaller pores and may block hydrocarbon flow. So a reservoir with high porosity but also high water saturation may still have limited hydrocarbon potential. This is why petrophysics is always about combining multiple properties, not looking at them one by one in isolation. A good reservoir is not just porous, it must also have favorable saturation and flow characteristics.